Namaste everyone. It's the seventh webinar on electrical energy storage overview, market needs, challenges, and the future roles. Organized by Electrical Engineers Welfare Association Nepal. I am Vinod Sharma, the executive secretary of this association. On this moment, I would like to welcome the president of Electrical Engineers Welfare Association Nepal, Mr. Rajendra Dhakal, and other executives of this association. I would also like to greet and welcome our chief guest and the speaker of this session, Professor Dr. Ahmed F. Zobaa from Brunel University, London. I would also like to welcome our today's special guest, founding advisor of this association and the deputy managing director of the leading power utility of Nepal, Nepal Electricity Authority, Mr. Ramji Bhandari sir. I would also like to welcome all the professor, associates, heads, and director of different organizations, universities, department, and also researcher and the student from many universities who are with us today. I would also like to welcome all our previous presenter of this season. I would also like to welcome all the viewers on Facebook Live from our Facebook page. Today we have our executive members, Bisam Vinod Khanal and Sandeep Dami, is the moderators as always. First of all, we are thankful to Nepal Research and Education Network, NREN, and Nirajan sir for hosting webinars for us. You are doing a great job helping us in moving toward the online learning. This episode is very special for us, not only because it is a final episode of this season, but today we have a webinar on very suitable and hot topic of electrical engineering from a very experienced and expert professor. Today is this is the last episode of our season 1. We are very grateful toward all our presenter of this session, and we want to appreciate them with a small certificate of appreciation. We also provide certificate of participation to this participant as soon as possible. We are very honored and thankful to our guest speaker, Professor Dr. Ahmed F. Zobaa, for providing precious time for us from his busy schedule. It was our special event. I was very excited for this event. I'm personally and from the side of our association really want to appreciate you. Now, I want to introduce our speaker with this short biography. So many of us already know him. Dr. Zobaa received his BSc, MSc, and PhD degree in electrical power and machine from Cairo University, Egypt in 1992, 1997, and 2002, respectively. He received his postgraduate certificate in academic practice from University of Exeter from the UK in 2010, and his doctoral of science from Brunel University, London, UK in 2017. He has spent 28 years in the academy at Cairo University, Egypt, University of Exeter in UK, and Brunel University, London, UK. Currently, he is a reader in electrical and power engineering and an MSc course director and full member of the Institute of Energy Future at Brunel University, London. His main areas of expertise include power quality, renewable energy, smart grid, energy efficiency, and lighting application. Dr. Zobaa is an executive editor for International Journal of Renewable Energy Technology and executive editor in chief for Technology and Economics of Smart Grid and Sustainable Energy and International Journal of Electrical Engineering Education. He is a registered chartered engineer, chartered energy engineer, European engineer, and international professional engineer. He is also a registered member of Energy Council UK, the Egypt Syndicate of Engineers, and the Egyptian Society of Engineers. He is a senior fellow of Higher Education Academy UK, fellow of Institute of Engineering and Technology, Energy Institute UK, Chartered Institute of Building Service Engineer UK, and Institute of Mechanical Engineering UK, the Royal Society of Arts UK, the African Academy of Science, and Chartered Institute of Educational Assessors, UK. He is a senior member of IEEE. Uh, now we will move directly toward the awaited presentation. There will be few time for question answer at the end of presentation. You can message us your question. We will take as many as possible, and also considering time. If you want to ask the question in your own voice, we will unmute you. For this, you have to raise your hand. Now, without consuming more time, I would like to request Dr. Ahmed F. Zobaa for his presentation.
Okay, so thank you so much. Good morning, good afternoon, good evening, everyone. I am honored to be with you today and invited by Electrical Engineers Association in Nepal to share my experience and knowledge in the topic of electrical energy storage in general, and specifically for overview, market needs, the challenges, and the future rules specifically for this webinar. Just to let you know briefly about my university. My university is Brunel University, London. As you see on the map, this is where I am here now. Brunel is a campus-based university situated in Uxbridge, West London, founded in 1966, home for more than 15,000 students from over 100 countries worldwide. We are the 25th in the top 100 under 50 years old universities. As a university comprises the 3 colleges, and I am in the first college, which is engineering, design, and physical sciences. Also, we have business, arts, and social sciences college, and health and life sciences college, plus we have a graduate school. Just to introduce this important and timely topic which I am talking about it today, energy storage is essential to balance supply and demand at fairly short notice. High levels for energy storage are required for grid flexibility, which is one of the important things we are looking for nowadays, and for the future, for what is we are hoping for smart grids. Secondly, grid stability. Thirdly, coping with increasing use of intermittent wind and solar electricity. Energy storage can be integrated at different levels of electricity grid, including generation level, where we can see that the energy storage can play for arbitrage and balancing and reserve power. Transmission level, where it can play with the frequency control, investment deferral. At distribution level, playing with the voltage control, capacity support. And finally, at the customer level, playing with the peak shaving, time of use, constant management. Energy storage, or generally electrical energy storage, will play a key role in enabling the world to develop a low carbon electricity system. Also, it can supply more flexibility and balancing to the grid, providing a backup to intermittent renewable energy. There are few available storage technology at present that are economic and visible for us, and we will see this shortly through the presentation. According to the latest IEA tracking report published in June 2020, around the globe, 2.9 gigawatt of storage capacity were added to electricity systems in 2019, almost 30% less than in 2018. Overall, the storage capacity installation rate in Europe slowed by 40% year on year behind the meter storage, outshone sluggish deployment of grid-scale application led by Germany, where over 50,000 systems were deployed through 2019 without any subsides. And this is the problem which the utilities are facing when they are not offering subsidies for the customers to highly penetrate the more renewable energy in the electricity systems. So this presentation will include the brief overview about the energy storage technology, including applications, case studies, main developments, market needs, current market, future market potential, the future rules and the challenges for energy storage, how to plan for any energy storage project, whatever in the distribution systems or transmission systems, including tools which we can use to do this, and finally to conclude the presentation. Starting with the technology overview, as you can see in this slide, we have different energy storage technologies, including mechanical energy storage, electrical energy storage, thermal energy storage, and the chemical energy storage. Starting from the mechanical energy storage, including the two types of the energy storage as potential and the kinetic energy, which include compressed air, pumped hydro, flywheel. Talking about electrical energy storage, we have two subcategories, including electrostatic energy storage and magnetic energy storage, which include capacitors, supercapacitors, and superconducting magnetic energy storage. The third, which is thermal energy storage, has two subcategories depending on the temperature. So we have low temperature and high temperature. This will include mainly the sensible heat storage and latent heat storage. And finally, chemical energy storage. We have three subcategories depending on chemical or electrochemical or thermochemical. And this include batteries, fuel cells, solar hydrogen, solar metal, solar ammonium, and solar methane. Just going through for the big projects in the world and talking about the hydropower, we can see that this is the number one project in the world, which is Three Gorges Dam in China. It has 32 turbines with a capacity of 22.5 gigawatt. In 2014, the dam generated 98.8 terawatt hour and had the world record. The second, which compete neck to the Three Gorges Dam, which is Itabo Dam, and this is on the borders between Brazil and Paraguay. And this dam has 20 turbines with a capacity of 14 gigawatt. And in 2016, the dam generated 103 0.1 terawatt hour and had the world record as well. Talking about pumped hydro storage, and this is a storage media of the potential energy, and where we can use it to store during the off-peak and generate during the peak demand periods. The biggest facility, which is Bass Country Pumped Storage in Virginia, United States. It has 6 turbines with a capacity of almost 3 gigawatt. As you see on the left-hand picture, this is the 2 reservoirs, because pumped storage wants 2 reservoirs with a head in between. So this is the 2 reservoir which has 30 gigawatt hour equivalent capacity. This is the biggest energy storage system in the world with 2 reservoirs covering 800 20 surface acres can store up to 3 gigawatt-hour storage capacity. In Europe, we have pumped hydro storage in Luxembourg, and this project has 11 turbines with a capacity of 1.3 gigawatt. Again, in the picture, you can see the upper reservoir, which is an artificial construction, and the river with the dam is the lower reservoir. This is the largest storage facility in Europe using this technology. In the UK, we have what is called Dinorwig Power Station, and it has 6 turbines with a capacity of 1.728 gigawatt. Dinorwig is operated not to help meet peak loads, but as a short-term operating reserve, providing a faster response to short-term rapid changes in power demand or sudden loss of power station. Simply speaking, let us talk that we have a national event, or say the final match of the Premier League or Champion League, whatever. Imagine how many millions of kettle in the halftime are on. You can reach up to 2 gigawatt just in 15 minutes, which is the halftime. So Dinorwig, this is the major rule for this power station. Just we are using it, and one of the names for this power station is called a TV pickup station. Talking about the compressed air energy storage, and this is the first power plant in Germany, constructed in 1978 with a round-trip efficiency of roughly 41%. It has a capacity of 60 megawatt charging and 321 megawatt charging. So let us talk about the technical comparison between all of these technologies. As you see in this table, we have the different characteristics which we will compare all of the technologies together. Talking about the response time, and as you follow the arrows, you can see that the electrical storage technology has a very fast response time compared with the other technologies. If we will talk about the capacity, you can see that the compressed air energy storage underground and pumped hydro and the capacitor energy storage, we can see that we have higher capacity which we can install using this technology. Talking about the runtime, you can see that the high temperature thermal storage and the mechanical storage having higher runtime compared with the other technology. So just one point we can conclude, we don't have ideal and optimal technology till now. Every technology has their pros and cons, and depending on your need, you can choose the best option for you. This graph just to give you idea about another comparison between the rate power and the energy for all of the different technologies. As you see, so again, let us talk about the discharge time. If you need short discharge time, seconds to minutes, you can find that the double layer capacitors, the super magnetic energy storage, and the flywheel energy storage can meet this option with energy to power ratio less than 1. If you are talking about medium discharge time, which means minutes to hour, so flywheel energy storage, lithium ion, lead acid batteries, sodium sulfur batteries, they can support this range with energy to power ratio between 1 and 10. And finally, and which we are still working on it and hard to get this option to have long discharge time, talking about days to months. How we can store the energy for a longer time. We're still working on this, but we have emerging technologies including hydrogen and the synthetic natural gas, which can support this range with energy to power ratio greater than 10. Excuse me. Another comparison, if we will compare power density in watt per liter against the energy density in watt hour per liter for all of the technologies, you can see this graph comes, and we can conclude that the higher the power and the energy density, the lower the required volume for the storage system, and vice versa. So if you are looking to have higher power density and higher energy density, you can see at the top of the graph, you are going to have a reduced volume according to this. But having lower power density and lower energy density, you can go to the bottom left side of the graph while having increased volume. And this is proved with two technologies which support this range for using pumped hydro storage and compressed air energy storage. Another comparison, if we will compare between the state of art against the nominal power for all of the technologies, you can see all of the technologies in this graph, and clearly from this graph, pumped hydro storage, compressed air energy storage, hydrogen, synthetic natural gas are the only storage technologies available for high power ranges and energy capacities. Also, energy density is rather low for pumped hydro storage and compressed air energy storage. So this is just to conclude all of the previous comparisons. And as you see, this is the major excuse me, can I ask who is switch on, unmute his mic to mute it, please? Thank you. So we have all of the major technologies in this table, and as you see, we list all of the advantages and disadvantages for each of these technologies. Again, as you see, every technology has pros and cons, and we have restrictions for the technology to make it optimal for all conditions. Let us go for the applications. What are the different applications of the energy projects? This graph gives you an idea about the capacity size needed for village, for a small town, for large town or city, and for regional and national. As you see, batteries, compressed air energy storage above ground, and maybe liquid air energy storage can support the scale from village to small town. Liquid air energy storage, compressed air energy storage underground can support the range from small town to large town or city, and compressed air energy storage, pumped hydro storage, which are well-established technologies evidenced for the higher scale between the city and the regional or national. We have problems with the technologies. If we are talking about compressed air energy storage and the pumped hydro energy storage, it requires mountains, so we have problems. Compressed air energy storage require caverns. So as we can see, these technologies are geographically limited. Talking about the batteries and above ground compressed air energy storage, they are very expensive. And as you see that the research and development are working hard to reduce the prices of the different battery technology which can support the grid in the future. If we will talk about the time scale for the applications of energy storage, we can divide this into two different applications. Talking about energy applications, this means longer time scale, larger amounts of energy. If we will talk about power application, this means shorter time scale and real-time control of the grid. We have different rules under each application. So energy applications means arbitrage, time shifting, demand charge reduction, time of use charge reduction, transmission and distribution upgrade deferral, and the grid resiliency. But while talking about power applications, we can have frequency regulations, voltage support, small signal stability, frequency drop, kinetic inertia, and the renewable capacity firming. What is the present status of these applications? On the utility use, conventional power generation, grid operation, and services, we have pumped hydro storage for time shifting and power quality. We have compressed air energy storage for time shifting and power quality. We have emerging power supply. We have off-grid systems which are called isolated grids. From the consumer point of view, we can see that we have uninterruptible power supply for large consumers, and this is well-known applications for decades. What about the new trends in applications? One of them, which is renewable energy generations, and we can see that decentralized storage system for increased self-consumption of the PV for photovoltaic energy, which we call it as kilowatt hour class. Secondly, talking about the wind, smoothing out for wind and maybe photovoltaic energy, and this type of application is called megawatt hour class. And this picture gives you idea about how this application applied in the world, and mainly in Japan. We have this wind farm with the total power output about 40 megawatt, and this output was smoothed and peaked by using sodium sulfur battery units, and gives you idea about how they connected the battery storage facility at the bottom of the picture to the wind turbines through the control systems, administrations, and the connection units. New trend of the applications as well, smart grids, and for the future distribution system, grid will become more active and will have to accommodate bidirectional power flow and an increasing transmission of information. So this picture give you idea about how the future grid looks like. Smart microgrids, and for flexibility in resisting outages caused by disasters, it is very important to deploy smart microgrids that's distributed smart power sources as an element in constructing smart grids. Simply speaking, we can localize the distributed generation in microgrid, and this small microgrid will become a part of the big grid. And if we make a smart grid, we will have a smart microgrids as well. New trend of applications, the smart house. The concept of the smart house is proposed in order to use energy more efficiently, economically, and reliably in residential area. So using your tablet or your mobile, you can switch on, switch off the heating while being out of your house. You can manage your use from the gas for heating or for electricity as well. So this is how it looks like the future of the houses. New trend of applications, electric vehicles. The emerging development of battery technology in recent years presents new possibilities with batteries displaying increased energy densities. And this picture gives you idea about the different abbreviations which we are calling nowadays. So we may see what is called vehicle to grid. We may see what is called vehicle to vehicle, and we may see to what is called vehicle to home. So all of these trends of application, we can see them, and this is what all of the distribution companies working on them now, and especially in the UK for the coming 10 years, because we announced that in 2033, our country will have 100% electric vehicles. This is not an easy task to host 100% electric vehicles, and also we have heat pumps. These types of loads, we don't know the exact nature or the exact load profile for these technologies. So the DNOs nowadays are enjoying their life in investigating how the load looks like in the future, and to forecast it and to estimate it. At the same time, it's a very green area of research for all of us as researchers. Let us go through some interesting case studies, and I share with you very interested case studies. This is happened in Chile in 2011. They have 544 megawatt thermal power plant in the town, and they developed 20 megawatt, 5 megawatt hour storage unit to perform as a critical reserve capacity. Again, another case study in Chile in 2009, they developed 12 megawatt, 4 megawatt hour storage unit using lithium ion batteries to perform as a standby spinning reserve capacity for them. Another case study in Chile in 2011, this facility has 98 megawatt wind power generation plant located in one of the states, Billington, that's built to supply more than 260,000 megawatt hour of renewable energy annually to BGM utility. So they developed a 32 megawatt, 8 megawatt hour grid energy storage to provide frequency regulation services using this technology. In Hawaii in 2012, 20 megawatt dynamic power resources using dry battery to integrate with 20 megawatt wind park. In Hawaii in 2012 as well, there is a Hawaii Electric Light Company had the technology required for the Big Island to integrate an even greater amount of renewable resources with its grid. So they developed 496 kilowatt hour energy storage system coupled with a 2-hour runtime, can be charged overnight during off-peak times, and has expected operating life of at least 15 years. In Missouri in 2012, this is a demonstration project, include 10 kilowatt wind turbine, 20 kilowatt solar, comprised of multiple solar panels and multi-tier battery storage, comprised of multiple electrochemistry. So they use different technologies with different power generation, and currently this system is being used to shave about 200 kilowatt from the 500 kilowatt daily usage of the facility. In California in 2012, the island microgrid has a peak load of 5 megawatt, which is served by Southern California Edison through a combination of 6 diesel generators and 1.4 megawatt of micro turbine. They developed 1 megawatt from a technology which is called the PureWave storage management systems, using sodium sulfur batteries, efficiently stores and release power from the island generators. In Canada in 2014, this remote town relies on 125 kilovolt distribution feeder provided by BC Hydro to supply its 300 residents with power. They developed a 1 megawatt sodium sulfur battery to may supply a reliable power to the town with which had frequent extended outages. In California in 2012, and this example for the flow battery, we can see this onion, Gills onions, operates an advanced energy recovery that went into operation in July 2009, convert all of the planned daily onion waste into a combination of renewable energy and cattle feed. So this is just to give you idea where the energy storage in the world, and as we can see that a lot of projects comes in from the United States, early 2010s, but nowadays worldwide, as we mentioned, we have more than about 3 gigawatt overall. What about the short-term technology development? So during the coming short period, we can see what is called innovative pumped hydro, and this is new generation of a variable turbine that will allow a very precise load following and will react in seconds instead of minutes. For the batteries, we can see a high reduction of the costs of batteries. For the medium and long-term technology development, we can see advanced pumped hydro, and this combine variable turbines with variable pumps and the new generators reacting in seconds. And we can see hydrogen, which will aim for long-term storage, more flexible systems, and for integrating energy storage with chemicals productions. We have we can say pilot projects because you are talking about few megawatts, but till now we still have the problem for the hydrogen, how you will transport it and how will you store it. This is still question marks for this technology. We can see advanced batteries, as we see introduction for the lithium ion and the nickel metal halide batteries, the emergence of the electric vehicles, including plug-in hybrid vehicles. For thermal storage, we can see the next generation of the compressed air storage with heat recovery, and we can see what is called liquid air energy storage. And this is just to share with you that we have a full operational 350 kilowatt, 2.5 megawatt hour as a pilot plant in the world from the liquid air energy storage, and this costed us 1.1 million pounds, and it is working now in Birmingham. This is an indicative layout for the biggest project will be in the United States for 20 megawatt, 80 megawatt hour systems. And as you see, the different components of the this system, and the area, they need area 22 meters times 66 meter to host this technology with this capacity. And this is this project, which is called Giga Plant, and this is the conceptual design of this plant, and this will be 200 megawatt power output, 1.2 gigawatt hour storage capacity, and this will cost about $230 million. Sorry, this is the project which will be in the US, but this project which we are working on it as well. This is one of the emerging technology or new technology, but we see that this will be the future of the energy storage, which is called gravel battery. As you can see, this technology made out of gravel. The battery consists of two large silos filled with crushed rock, and the electricity is stored as a temperature difference between the two chambers. So as you see, during the discharging and the charging, we have different temperature, the temperature difference in each silos where we can store the heat energy. The company which developed this technology, they state the advantages of this technology, including ground trip efficiency as high as 80%, low levelized cost of storage. We can deploy it anywhere in the world, designed for 2 to 5 megawatt per unit, 8 hours of storage, environmentally friendly, highly sustainable, significantly safer, cost over 25 years are estimated to be about $50 per megawatt, while the pumped hydro is about $65 per megawatt hour. So as we see, this technology will compete with all of the existing technologies of the energy storage. They made a study, and the company which is called Isentropic. If you remember at the beginning of this presentation, I mentioned the biggest pumped storage facility in the world, in the Basque Country, in Virginia, and this has a capacity of 30 gigawatt hour capacity. Isentropic says a pumped heat storage plant, which you can see it at the top of the right-hand side, the pictures, has the same capacity and would occupy 1/300 of the area of this Basque Country. So imagine how we will have a very compact design of energy storage, which can host a storage capacity equal to the Basque Country pumped storage technology. So as I mentioned, we have a lot of emerging technologies coming, and the future is very bright for the energy storage. What about the market needs of the electrical energy storage? We have almost 5 needs. We need for lowering energy costs, and this gives you idea about the demand in different countries, including Japan, Germany, France, Italy, North Europe, and BGM. During peak periods when electricity consumption is higher than average, power suppliers must complement the base load power plants, such as coal-fired and nuclear. During the off-peak period, when less electricity is consumed, costly type of generation can be stopped. Energy storage can lower electricity costs. The second need, which is flexible supply. So power generators need 2 essential functions in addition to the basic generation function. The first, which we call it kilowatt function, and the second, which we call it as a frequency control function. Solar and wind don't possess both a kilowatt function and a frequency control function unless they are suitable suitably modified by a negative power margin or a phase shift inverter. And this happened in Germany. Germany made this modification and they call it as system services, which must be implemented in large wind power generators. And maybe you remember in 2017 or 18, we had in the press that Germany has negative energy costs due to increase in the generation from the wind and the solar at the same time. The energy price comes minus two, as I remember, minus 200 euro per megawatt hour. So imagine that the utility is selling the energy and giving money to the customer who is consuming their energy as well. So this is one of the problems, and we can solve it as Germany did. Electrical energy storage is expected to be able to compensate all of these difficulties with a kilowatt function and frequency control function. The third need, which is continuous supply, consumers' locations are often far from the power generating facilities, and this sometimes leads to higher chances of an interruption in the power supply. Also, we have natural disasters, lightning, hurricanes, which will make failure to our networks as well. So the energy storage will help users when power network failures occur by continuing to supply power to consumers. The fourth need, avoiding congestion in power grids. And this is one of the interesting needs. In the process of balancing supply and demand, power congestions can occur. Utility companies try to predict future congestion and avoid overloads. So the energy storage, we can establish it at appropriate sites, such as substations at the end of heavily loaded transmission lines, and by then it will mitigate the congestions by storing electricity while transmission lines maintain enough capacity and using it when lines are not available due to congestion. The fifth need, which is mobile applications, and as we can see that the energy storage can help as a mobile applications and in the isolated energy, and they can solve the problems with their mobile applications and the charge discharge capabilities. One of the needs, which is the future low carbon energy systems, and this picture gives you idea how the future grid will look like. So we have decentralized energy storage among the grid with the different technologies. So we are working on this now. To conclude, this market needs two characteristics of electricity generate the market needs for energy storage. First, electricity is consumed at the same time as it is generated. And secondly, the places where electricity is generated are usually located far from the location where it is consumed. We solve these problems using the energy storage. And also, there are major emerging market needs for the energy storage, including utilizing more renewable energy. We are hoping to reach 100% renewable energy in the future and less fossil fuel, smart grids, and management and control hierarchy. What about the current markets of the energy storage? These coming slides gives you idea about how it looks like the technology developments and the current market. So this picture graphs gives you idea about the different technologies, and we can see that 98% of the technology development comes from the pumped hydro storage. This is a very busy graph, but gives you idea what about the batteries. And as you see, we overall in the globe, we can see we have 18% lithium ion, we have 24% sodium sulfur, we have 7% nickel cadmium, and we have advanced lead battery acid batteries and what is called lithium iron phosphate battery as well. This is another graph, gives you idea about the thermal storage from the chilled water thermal, the heat thermal, whatever low or high. And you can see in the globe, we have 77% from this technology comes from the molten salt thermal storage. And especially we use it in the concentrating solar power generation. For the compressed air technology, we can see that 99% of the projects in the globe comes from the in-ground natural gas combustion compressed air. If we look to the number of the operational projects with the technology, we can see that we have more than 360 project comes for the battery. The second pumped hydro with almost 300 projects. The third is the thermal. And as you see, we still work on flywheel, capacitor, hydrogen, compressed air to have it more and more on the grid scale. This is the battery technology. And as you see, the lithium ion battery and the lithium ion phosphate. So in general, lithium ion, this is the technology which we are working and using it a lot on the grid scale. For the compressed air technology, the most technology comes from the in underground, or what is called in-ground compressed air. Again, this is for the thermal, and we can see that we have more than 100 operational projects comes from thermal energy storage. Talking about the costs, as you can see, this is the different costs of the power in dollar per kilowatt and of energy in dollar per kilowatt hour. The highest is the hydrogen, as you see, and it comes in place. The second is the flywheel. So this is how we are working now to reduce the cost of the different technologies of the energy storage. Just to meet the time, the future market potential, we can see that some US states have world-leading energy storage incentive program, which has adopted a 1.325 gigawatt target by 2020. China on track to have over 10 million electric vehicles on its road by 2020, but we should consider what is happening nowadays from the pandemic. So this may be delayed, but this is the latest records. In Japan, they have an ambitious target to produce half of the world batteries by 2020. Germany will drive adoption of energy storage with a target of 27%. And the UK, our target is to have 12 gigawatt of battery storage by the end of 2021. It is achievable and will support post-Brexit growth. The potential market in the future is mainly driven by the extended use of renewable energy sources, the transformation of the energy sector, and including new applications such as electric mobility. The most promising market is conventional stabilization, where pumped hydro storage and compressed air energy storage are applicable. Another attractive market, which is balancing energy, and this corresponds to adjusting power supply to meet demand that fluctuates within short periods. What is the future rules of the energy storage? So this picture gives you idea the scale of the power and which rules we can use for the energy storage, starting from the bulk storage, which is a great scale greater than 50 megawatt, and ending by the customer led storage, which we call it behind the meter, less than 100 kilowatt. And we can see that we have different rules which can support, and I mentioned it earlier, using energy applications and power applications. Let us now to briefly conclude the future rules from 3 different points of view. So from the utility point of view, we can see these key rules in bold in the future. Time shifting, energy storage can decrease the gap between daytime and nighttime. For power quality, energy storage can provide frequency control function as well as it can be located at the end of heavily loaded line to reduce the congestions. Making more efficient use of the network, battery can be installed at appropriate substations and also to mitigate the congestions, as well as deferring any reinforcement of the network. Isolated grid energy storage can supply stable power to consumers, and finally emerging power supply for protection and the control equipment. If we will talk from the point of view of the consumers behind the meter, so the energy storage can support time shifting and cost saving by using energy storage to reduce peak power needed from the grid during the day and to buy the needed electricity at off-peak times. It can be used as emergency power supply. Also, it can be used for electric vehicles and mobile applications, supporting what is called vehicle to home and vehicle to grid, which I mentioned them earlier. From the point of view of renewable energy, energy storage can support for time shifting, effective connection to grid, and long-term solution to duct curvature. What is, just to briefly let you know what is duct curvature for who doesn't know this. This was happened in California as the problems raised and make a concern worldwide. In 2012 in California, the load curve was bobbing along like normal camel. And as you see, this is the normal load curve. And if we see, we can see the camel very clear. And this is the load curve which any utility would like to have. We always, as utilities, like to see camel, which is manageable and secure. But in 2013, California ramped up the use of the solar, and you can see things that started to change. From the camel, the load curve becomes as a duck, as you see in this graph. If we remove the duck, you can see this is the load curve, which the utility doesn't like to see. Why? We have ramp need, as you see on the right-hand side, about 13 gigawatt in 3 hours, and at the same time, over generation risk at the bottom of the curve, which led to negative energy prices as happened in Germany due to a storm and high and very clear sunny day in there. So what is wrong with a duct? Steep, tall ramps, overgeneration and curtailment, and the frequency responses. The two big and long-term solution to solve the problem comes from a high level of solar in your grid is using energy storage or interconnections. As you know that here in the UK, we have too many interconnections with our neighbors, as well as we changed the policy and we started to include energy storage in our grid as well. What about the challenges of the facing energy storage? We have different challenges, including technological, economic, market and regulatory issues, strategic, and the recommendations actions from the latest tracking report comes from the IEA in June 2020. They recommended these actions to face the challenges. Place flexibility, not individual technology, at the core of a policy design. Continue to revise the status of storage in regulatory frameworks. Expand the role of storage in ancillary services and the flexibility market. And finally, make priority for the most easily accessible applications. So we're still working on the energy storage, and one of the challenges really which we need to focus on it, the regulatory frameworks. Ending the presentations for how to perform planning study and tools used for energy storage projects. So to study, this is recommended or one of the methodologies which can be used for the planning. So starting from the target application area, which applications you want from the energy storage, and then check the strategic market scenarios, system model, interconnection, target constraints, then get the optimum storage size and site, interconnection studies, economic benefit analysis, revenue stacking potential, and then you can conclude the project portfolio. Depending on where you are in the transmission network or in the distribution network, so this just flow give you idea how to perform planning study if you have a transmission network. So you can perform the siting analysis using Power World, for example. This is not the recommended one, but just as an example, using the two tools of this Power World, and from which you go using custom tools, which one of them Quanta technology tool set, which you can perform all of these different studies and solutions, and then you can check the production costing using system-wide evaluation, and finally ending with project economics, checking the net present value, checking the benefit cost analysis, checking the managerial option value, and this can be done using, for example, Microsoft Visual Basic. On the distribution level, you can use, for example, SIAM, Python, Synergy software to check the T&D deferral times years, and check as well the battery energy storage system size, from which you can do the simulation using MATLAB for the day ahead economic dispatch. Then you can check the system wide, or you can evaluate the system wide, and ending with the cost analysis again using the Microsoft Visual Basic. After this long presentation, I will end with this interesting statement, and the statement states a next generation smart grid without energy storage is like a computer without a hard drive, severely limited. Just to highlight on one of my books on energy storage published by IET in 2018, and this comprehensive work addresses current and the future rules of energy storage, prospects and the challenges in the generation, transmission, distribution, and the customer level of the grid. I thank my co-editors, Professor Paulo Ribeiro from Brazil, Dr. Shadi Abdelalim from Egypt, and Dr. Sarah Afifi from Scottish and Southern Electricity Company in the UK. And also I thank to all of our international contributors who contributed in this book and get it published. Thank you so much.
Thank you, Professor, for your presentation. Now we will look for a question from participant. I will take one by one. There is one question from Chun Singh. I am going to read it, Professor, for you. Question is, what is the current and future economic perspective of installing energy storage at home in UK? How can energy storage be more attractive to home owners? This is question by Chun Singh. Professor, you are muted. Sorry.
Yes, sorry. Not only in the UK, but worldwide. You know, sorry to say I am human, but human being is a crisis for the utilities. Okay, once a human being involved in anything, it will be a problem. And this is one of the problems for the smart grid in the future. You know, how you will manage to let the customer switch off his washing machine now. Some will accept, some will not. Okay, the same. If the human being don't see benefits from what they will do, it will be a problem. Germany passed this and led the globe for having a lot of photovoltaic homes, but generally, if you don't offer subsidies or incentives for the people, they will not go ahead and follow you. We issued and we used what is called the feed-in tariff, and this helped a bit in the UK and let the people start to have renewable power generation, and as well as once you have renewable power generation, you need the storage to store this energy. So simply to answer this, without incentives, you will not encourage the people to install renewable energy or energy storage at their homes. But we are working on it, and you don't know the future, everything will be changed. I hope this question.
Thank you, Professor. Now we have another question from Susan Acharya. How low-cost energy storage could be useful for large power system? What could be the possible AC storage system? I think it was in your presentation, but Professor, do you want to add anything more?
We cannot say energy storage system. Each technology has its cost, and I presented it in the presentation. We are working heavily nowadays on the batteries. As you know, we have the well-known battery, which is the lead acid battery. We have lithium ion, and we reduced its cost a lot comparing with the previous years. We have a problem with the lithium ion, as all knows that, which is called serial runaway, and you heard about many projects, you know, comes into fire in South Korea recently, and they shut down too many energy storage projects temporarily. We are working on advanced lead acid batteries, we are working on advanced lithium ion, trying to get the cost more and more. We have new technologies, which is zinc batteries, batteries. So again, there is no specific answer to say what is the cost of the energy storage system. You are talking about a specific technology. You can see how we are from the others technology.
Thank you, Professor. Now we have another question from Nabil Mohammed. He's saying, thank you, Professor, for this informative webinar. My question is in your viewpoint, what is the most promising storage for future smart grid? Additionally, do you think S2 storage will overcome lithium-ion batteries?
From my perspective, I can see that the battery is the technology which will lead the world. You know, lithium ion. This is the most use of the battery technologies. I am talking about the grid scale. Hydrogen, we solved the problems facing the hydrogen, how you will store it, how you transport it. It will be easy life and economic life, because imagine how many gigawatts of offshore winds you have in the world, where you can use this offshore power to generate hydrogen. Then you can transport or transmit the hydrogen into onshore, from where you can use it. Again, we are working heavily on the concentrating solar power. So molten salt technology is promising for this kind of technology, which is thermal energy storage. So the future again is open, and we are working on the different technologies to get more. And as you see, so in my presentation about the graphene battery, again, this is one of the emerging technologies. This is not only the ones in the world. There are many, you know, prototyping and for emerging technologies didn't come on the manufacturer scales. But again, to confirm my point of view, I see the battery is the leader. So this, we will not change our mind about the battery, but I think no technology till now, as we have in our pocket, there is no technology will compete with the batteries.
Thank you, Professor. Now we have another question from Mohammed Amin Raza Binedhart. What is your opinion about auxiliary service of battery energy storage, for example, reactive power compensation?
Yes, this is what we need. We don't use, as you see, the future rules of renewable energy, it will play in different rules, mainly for the frequency regulation and the control. It will play a very key role for it. Reactive power compensation, yes, we need reactive power compensation, and mainly for the solar power generation, we can see that the inverters can support this kind of ancillary service plus the storage, because once you have lots of reactive power storage, we have a problem in the grid. But again, the energy storage can play whatever on the energy application side or power application side to support this. The future of the energy storage is not a storage media. This is mainly for any ancillary services in the grid.
Thank you, Professor. We have another question from Taheri Bagheri. His question is, are there any challenges for maintenance of batteries?
I didn't include the maintenance in my presentation, but again, yes, you need a lot of precautions, safety issues, standards, you need guidelines, you know, and there are many organizations are working for this, for different technologies of the batteries, how to install, how to design, how to maintain, you know, these batteries, because high risks comes from any type of batteries. You know, you have hydrogen problems, you have fire problems comes from the thermal runaway and all of this stuff. So yes, depending on the technology, there are standards for maintenance, and depending on the size, there are many guidelines we can see worldwide where you can install. Let us say if you are talking about uh, 70 megawatt hour energy storage. So there are standards in NFPA mentioned stated to you that is install this technology. I don't remember the number for number of feet above the street side in your project and so on. So yeah, there are a lot of things around these questions. It needs another webinar to talk about the maintenance of batteries.
Thank you, Professor. We have another question from Milton Nag. He is asking, at which level of electricity network should storage be integrated?
Any level. And I think it is clear in my presentation, it can work at the different levels: generation, transmission, distribution, the customer level. And for each level, there are rules where the energy storage can support the grid.
Thank you, Professor. Likewise, we have another question from Santosh Adhikari. Can we maintain both reliability and economically beneficial from ESS compared to grid system?
No. We don't have optimal and ideal solution from the energy storage. Okay, you must accept some cons or disadvantages for the technology you are using. So simply speaking, my point of view, you cannot have both. Yes, you can make it more reliable, but you will not get 100% reliable, 100% economical. No.
Thank you, Professor. Similarly, there is one question from Shiva Prasad Dahal. Is it possible to storage AC directly without conversion into DC?
Yes, other technologies you can use, you know, from the AC flywheel, you don't need to convert into DC to store. So you can take the AC straight away to store it without converting to DC. But the conversion is not a problem, you know. Yes, because the most common technology batteries mean DC. So that is the reason that we always convert. But other technologies, for talking about the flywheel, yes, you need the AC. You will not be able to use flywheel for longer periods of times, and it's only up to 8 hours, and that's it for the flywheel. So yes, there are technologies you can use without conversion into DC.
Thank you, Professor. There is another question from Mohammed Amit. Do you think that combination of ESS such as BESS and supercapacitor can be used more in future? And similarly, a question from Muhammad Bilal. He is also asking why we cannot consider supercapacitor as energy storage. I think both questions are similar, so I asked you at the same time.
Supercapacitors is energy storage. Who said that we cannot consider supercapacitors as energy storage? It's an energy storage technology. For the first question, yes, and there is a pilot project to use batteries and solar capacitors. To avoid the cons again of the batteries, we use the super capacitor to compensate these cons. So hybrid, this is what is called hybrid energy storage. So one of the options which you have, yes, you can have hybrid energy storage, which is a combination of different technology to reach to your needs. And this is which I mentioned, the planning study. During your study, you can get the optimal, okay, size and siting for your technology.
Thank you, Professor. We're moving to another question. There is one question from one of our participants. For hybrid energy storage, what is the optimal combination?
Again, it is open. We have different technologies. So what you need to do is check your needs, and depending on these needs, you can get the appropriate combination which will meet your needs. So it's not, there is no answer for what is the best. This depends on what is your need and what is your desire or your requirement. Then we can answer this question.
Thank you, Professor. There is another question from Ilyas from Algeria. He's thanking you for your presentation, and our question is the duration of charging battery, is the duration of charging batteries can represent a drawback for ESS?
No, the charging and discharging, this is number of cycles. Again, depending on your requirements, you can choose the best option for depending on how many cycles you want, depending on your load profile, a lot of things. But again, the planning study can let you choose which battery it can meet your requirements.
Thank you, Professor. I think we cannot take more question due to time restriction. Now we are going to another segment. Now we are almost at the end of session. Summarizing this season, we have conducted 7 episodes in this season 1. There are 7 episodes in this season 1. I am going to describe the name. First was a grid-connected PV system designed using heliscope by Sandeep Setsan. Second was a lightning protection necessity in Nepal, jointly presented by Sabuddin Khan and Devesh K. Jaswal. And third one was engineering and entrepreneurship by Mahesh Mahato. And fourth was a detailed hydropower modeling and simulation in an open source library by Madhusudan Pandey, his researcher, University of Southeastern Norway. And fifth was mini grid status, challenges and scope by Ashish Shrestha, lecturer, Kathmandu University, Nepal. And sixth was microgrid energy from inside out by Professor Dr. Joseph Gurero from Aalborg University, Denmark. And the seventh is electrical energy storage overview, market needs, challenges and future role by Dr. Ahmed Zobaa. Now we are also delighted by the presence of the founding advisor and deputy managing director of Nepal Electricity Authority, Nepal, Engineer Ramji Bhandari sir. So before going to the another segment, now I would like to request respected Ramji sir for some valuable words for this event and our season.
Yes, thank you, organizer EM for inviting or attending me on this webinar. for energy storage technology. And I will also like to thank the presenter, Zobaa, for this new technology, energy storage technology, which can be implemented, in various areas of the world. And we have seen a number of technologies that have been already been established in US, Canada, China, Japan, and everywhere. He has shown the different energy storage technology with electrical, mechanical, chemical, and different different aspects. And according to him, we find that the battery technology is mostly widely used in all over the world, whereas the hydrogen technology is lesser because of because of chemical, because of nuclear problem, because of security reasons. Hydrogen is most difficult, according to him, and battery technology is used all over the world. And also he has explained the variable turbine for the innovative pumped storage plant also. And there are also small technologies like small capacities technologies, 200 kilowatt modules of batteries and sodium sulfur, the different types. So I would like to thank these are all the new technologies that hasn't been introduced in Nepal grid system. So we have known very many things regarding these smart technologies. And as the deputy managing director and the utility of NEA, I would like to tell something. I would like to introduce something about the Nepal and Nepal electricity systems. In Nepal, it was started around 110 years ago. The electrical energy was established and installed from the Forping hydropower plant. And now today's date, the installed capacity is around 1,396 megawatt. The small capacity, small system, we have a small system and have a peak demand of 1,407 megawatt. In terms of this energy storage system, we have just the Nepal Electricity Authority utility of only one utility in the Nepal is starting to introduce these battery storage system BESS technology from our energy storage department, energy efficiency and loss reduction department. We have just started last year wanted to try to install this BESS systems in Nepal, and we have planned to install those planned in off-grid systems, just like one of our partners from the USA, Himalayan Clean Energy Power. They came here, and we have talked and we have prepared some document about the off-grid BESS technology to install in those areas where there is no electricity. Just like we have found some places in Kalikot where there are small micro hydro plants. Those BESS can be charged at the daytime, and in the evening that can be discharged, and the electricity can be supplied to the consumer. We have planned, we have think, and we are approaching to this storage technology in NEA itself in the coming year. Besides that, we are also using the clean energy hydropower, and our as I said that it is 1396 megawatt, and most of the power generation in Nepal is all from hydropower, water-based energy. And in the coming year, the government and the Nepal Electricity Authority has planned within 2 years we have a plan that is in 2023 and up to 24 we have planned to have a 5,000 megawatt capacity of the system, and we also have a plan to have a good distribution system, transmission systems in order to consume all these loads by our. But besides that, also we are also trying to have regional market concepts on the electricity power evacuation also, and for that we are doing we are having a negotiation. We have a talk with Indian power trade company to sell our electricity, more energy that we generate in the coming years shall be evacuated to India, or maybe in the coming year it maybe we have also one of the agreement with the Karnali Power with the Bangladesh regional. We have also gone for the regional trade market also, regional trade market policy also. So on that basis, though we have only one hydro energy based systems, and we are planning to have the solar. We have added 66 megawatt of solar energy in our systems in the coming year. We have a PPA. We have a signed power purchase agreement with them. We have signed PPA agreement with them, and we are having a mixed generation systems in our two also. And we also have a plan to have these battery storage systems in major governmental offices, just like Singha Darbar, Rashtrapati Bhavan. We have planned to install those 1 megawatt, 2 megawatt capacities, the BESS technologies, battery storage technology on these areas also. And any also starting the one of the pumped storage systems there, that is Rupa Begnas pumped storage systems around 150 to 200 megawatt capacity, maybe, I'm not sure. And the presenter by Professor Dr. Zobaa, he gave a lot of technicalities on energy storage systems, and that we have not adopted or introduced in Nepal till now. But we have a plan. We have policy to introduce all these things. And lastly, any questions or any queries from the participant sides regarding the what is the policy, what is the NEA planning to do on the electricity market or electricity generation or electricity distribution. For this, I can share with you about it. And finally, I would like to thank this committee, EEM, or what EEM committee, Electrical Engineering Provincial Pokhara chapter. I would like to thank them to invite me on this webinar to hear about this new technology and to share my views regarding the Nepal Electricity Authorities plan for the future in shortly. Thank you.
Thank you, sir. Thank you, respected Ramji sir, for your words and a brief description on the status of energy storage system from the side of our only utility, Nepal Electricity Authority. And we will always appreciate your efforts, love, care for our association, and we are fortunate to have you as a mentor and love to move on your guidance.
Vinod,
Uh,
I think there is a one question from someone about regarding the electric vehicle. Is it?
Yes, sir. There is one question from Sanjay Raj Timil Sinha. I will take it. My question is for Ramji Vandari, sir. Dear sir, as looking into the development of electrical vehicles, why it is not so developed in our country? Also, government is not encouraging so much on the use of electric vehicle. What can be the role of NA for this question?
Yes, Ms. Timil Sinha, Sanjay. Uh, it's a good questions that we are from the next year. I think we are having a large amount of generation. So we NEA we either NEA has to sell this electricity to its consumer, or it have to be sell to the regional markets. So on that perspective, NEA has planned for the electric vehicle in Kathmandu. So for that, the government of the Nepal government has planned to establish the charging stations facilities in the country. So NEA's business is to sell the energy. That's why the energy the electric vehicles, energy vehicles for the public. Let us say the buses are procured by the Ministry of Transport. They have prepared the technical specification for the technical specification of the buses. In the last year, as I know, they are preparing, and the government has planned to have 300 electric buses in Nepal. In last year they have planned, but due to the COVID impact, it is delayed. But NEA has already been tendered the 50 charging stations for all over the Nepals, and priority basis we will establish all those charging stations, and after that maybe from the private sector, maybe from the public sector, the energy consumption will be increased. Initially will be increased. The government has planned, they have a plan to have 20% electrical buses within electrical vehicles within 2020, according to the plan and policy of the government. But it was not met. But because we know that we have only around 600 to 700 private electric vehicles in Kathmandu Valley, four-wheelers. Maybe in thousands numbers, the two-wheelers are more than that. We have a plan. We have to go for the green energy consumption. So this electric vehicle is the must. And NEA is also planning. NEA is also going for these technologies. Just like we are changing all these solar light by smart light and others also. Thank you.
Thank you, sir. We are not taking any more question due to time restriction. We will arrange a separate webinar for this topic also. We are also encouraged by with the presence of our Gandaki province chief of Nepal Electricity Authority, respected Eknath Tiwari sir. We are also thankful for him. Now, especially thank you very much, Professor Dr. Ahmed F. Zobaa, for giving time for us and sharing your experience work for us. We are very grateful to you, and we are fortunate to have you in our webinar. It is a great experience for all of us. Now, with the permission of our president and our special guest, I would like to provide our presenter certificate of appreciation. Now I'm going to share my screen. I think it is visible to all of you. I'm going to read the certificate of appreciation. Electrical Engineers Welfare Association Nepal certificate of appreciation. This certificate is proudly presented to Dr. Ahmed F. Zobaa for sharing his valuable knowledge as a guest speaker in the webinar on electricity, energy storage overview, market needs, challenges, and future role. Now, I would like to request Professor Zobaa for his concluding words regarding this webinar.
Okay, thank you so much for hosting me today and to present and share my knowledge regarding and my experience regarding electrical energy storage. Thank you so much again for this certificate. I am honored to have it from the Electrical Engineers Associations in Nepal. Happy to contribute in the future in more topics and to share experience with your engineers and maybe after the pandemic, me visiting Nepal and to meet face to face. Thank you so much and have a nice weekend for you.
Thank you again, Professor. It was a great experience. So we look forward hearing from you in future too. We will now we will mail the certificate of appreciation to all our presenter of this session. Now we will provide the recorded video of this webinar for our interested participant. We will also provide a certificate of participation to registered participant as soon as possible. We will mail you. Again, thank you, Professor, and thank you all the guests. Thank you all participants for being with us throughout the season. See you in the next session. Good day. Thank you.
Thank you. Bye.